know that the nucleus of some galaxies can outshine millions of stars in the galaxy combined together? It's true. Welcome to the mesmerizing world of active galaxies. Get ready to dive deep into the astonishing realm of active galactic nuclei, or AGN for short. Let's begin. Active galactic nuclei, or AGN, are galaxies with a very powerful and often bright nucleus. An active nuclei is so bright that it dominates over the luminosity of all the stars in the galaxy combined together. As a consequence, these active nuclei can be observed to very high redshifts and act as a probe for exploring the early universe. As shown here, the radiation from an AGN spans the entire electromagnetic spectrum from radio to gamma ray wavelengths, such that the energy per logarithmic frequency interval is almost constant. In contrast, the emission from a normal galaxy usually peaks in the optical or mid-infrared wavelengths. AGN come in many different flavors. These are some of the commonly mentioned active galaxies in the literature. In this two-part series, I will briefly describe many of them, mentioning their similarities and differences. Then, I will discuss why some astronomers believe that all these different classes of active galaxies can be unified into very few categories with genuine differences in their intrinsic properties. In 1943, Carl Seifert reported a class of a small fraction of galaxies with very bright nuclei. These galaxies are a source of broad emission lines produced by atoms in a wide range of ionization states. The nuclei of these galaxies are very bright, almost like stars, and overwhelm the stellar light from the surrounding galaxy. These are now known as the Seifert galaxies. They are further classified into Seifert 1 and 2s and sometimes as intermediate Seifert types 1.5. Only a very small fraction of all field galaxies are Seiferts. Most Seiferts are spiral galaxies. The type 1 and 2 classification of Seiferts is based on their spectral properties. The type 1s have broad emission lines like these. They can be allowed lines such as the lines of hydrogen and helium, or forbidden lines such as oxygen 3. They also have narrow allowed lines, although even the relatively narrow lines are broader than the ones observed in the spectra of normal galaxies. The categorization of transitions originate from the quantum mechanical transition probability. The probability of the excited state in an allowed transition is the lowest at around 1/100th of a microsecond, and in the forbidden it is the longest at around 1 second. The forbidden transitions are not observed on Earth due to the presence of higher gas densities. They are denoted by a square bracket around the species, such as an O3. The transition probability of a semi-forbidden line, such as carbon-3 line, lies in between the two and are represented by a single square bracket on the right. Doppler broadening estimates indicate that the narrow lines originate from source with a typical velocity of 1 to 5,000 km per second, while the forbidden lines correspond to speeds of around 500 km per second. Seiferts generally have a featureless continuum devoid of any lines. In Seifert 1s, the small nuclear region often overwhelms the combined light from all the stars in the galaxy. Some Seiferts are found to show broad and narrow lines and therefore are labeled as type 1.5. Both Seifert types 1 and 1.5 emit X-rays, which is usually very variable in nature. The Seifert 2s are relatively less luminous, do not usually emit X-rays, and have narrower lines. The spectra of a few Seifert 1.5 galaxies changed to Seifert 2s in a matter of years, although the broad H-alpha line usually persists in their spectra. Radio galaxies are another class of AGN. Cygnus A was the first radio galaxy to be discovered. It is a peculiar-looking central dominating galaxy with a dust ring surrounding its center. At a distance of around 240 megaparsec, Cygnus A is very far, given that it is the third brightest radio source in the sky beyond the Milky Way, the Sun and the Cassiopeia A supernova remnant being its predecessors in terms of radioluminosity. This implies that Cygnus A must be emitting a lot of radio radiation to be detectable at such a large distance. As shown here, radio galaxies are powered by a central supermassive black hole feeding on surrounding matter. Some of this matter is ejected in opposing directions along the axis of rotation of the black hole in the form of powerful relativistic jets. These jets are launched with velocities close to the speed of light and travel vast distances away from their host galaxies. They emit radiation predominantly at radio frequencies but also emit across the entire electromagnetic spectrum. Jets have a major impact on their surroundings. They can significantly heat their environments, influence the star formation rate, and limit the growth of galaxies. Just like Seyfert's, radiogalaxies are subdivided into broad-line radiogalaxies and narrow-line radiogalaxies corresponding to Seifert type 1s and 2s respectively. The broad-line radiogalaxies have a bright star-like nucleus surrounded by a faint hazy envelope, while the narrow-line radiogalaxies are giant ellipticals dominating the centers of groups and clusters. But despite the similarities, they are different galaxies intrinsically because while radiogalaxies are elliptical, most of the Seifert galaxies are spirals. Although Seifert nuclei emit some radiation in radio, in comparison to radiogalaxies, they are relatively quiet at radio wavelengths. A radio galaxy may display extended radio lobes such as those observed in Cygnus A. These lobes are 17 kiloparsec each in diameter and around 120 kiloparsec apart in projection, and yet it is not a very large size compared to many other sources in the radio sky. For Cygnus A, we can also observe the central core and the narrow collimated jets feeding the lobes. Some or all of these features may be observed in radio galaxies. Around half of the strong radio galaxies and 3/4 of the weak radio galaxies have jets. Usually, only one jet is observed in strong sources, while two-sided jets are observed in weaker sources. One of the main reasons for this being that the strong sources can be observed at large distances, hence a weak counterjet may not always be detectable. As seen in these examples, these jets can span large distances, sometimes going beyond the scale of galaxy clusters. Let's look at a few famous examples from our neighborhood. M87 is a bright giant elliptical galaxy in the Virgo cluster, also known as Virgo A to radio astronomers. Its 1.5 kiloparsec long jet seen here was first observed in optical images in 1917. This dominant jet in M87 is also observed in X-rays and radio wavebands. The composite image of X-ray and radio emission of M87 shows that the jet originating at the center ends in the radio lobes with hotspots at either end. The X-ray luminosity of M87 is around 10 to the power 36 watt, which is 50 times more than its radio luminosity. Deep radio images also show evidence for a counterjet ending in the other lobe, which is opposite the dominant jet. Do you remember the 2019 observation of the first ever black hole observed by mankind? Well, it was observed using multiple radio telescopes around the world in this very galaxy, the M87. At 4.7 megaparsec from us, NGC 5128 or Centaurus A as it is popularly known is one of the closest AGN in the nearby universe. It is an E2 elliptical galaxy with a magnificent dust lane girding its center as shown in this composite image. Just like M87, Cen A also has jets extending from its nucleus all the way into the giant radio lobes. The jets of Cen A can be seen at optical, radio and X-ray wavelengths. When observed at radio frequencies, radio jets can be broadly classified into two categories based on their large-scale appearance, FR Type 1 and FR Type 2 respectively. These classifications were proposed by Fanaroff and Riley in the year 1974. FR2 radio galaxies have powerful jets which remain highly focused before terminating abruptly and inflating lobes of highly turbulent jet material. The regions of intense radio emission where the jets terminate are called the hotspots. FR2 jets are brightest at their leading edges. FR1 radio galaxies, on the other hand, have weak jets that are relatively broader and display significant wiggles along their lengths. The jets smoothly transition into curving plumes. The jets of FR1 sources are brightest close to the host galaxy from which they are launched. FR1 sources often exhibit two jets, while FR2 sources usually have one strong jet only. Now it is also well known that FR1 sources have 1.4 GHz radio luminosity below 10 to the power 25 watt per hertz, and those above this value are inevitably FR2 sources. Quasars are also FR2 sources. A small fraction of observed radio galaxies are classed as winged radio galaxies. Winged radio galaxies have two pairs of radio lobes, the primary and secondary lobes. The secondary radio lobes are called wings and are misaligned with the primary lobes, resulting in the unusual large-scale appearance of these galaxies. If the wings are located symmetrically on either side of the host galaxy and the primary lobes and wings are almost perpendicular to each other, then this gives a distinct X shape to the system. These X-shaped galaxies are a subclass of winged radio galaxies discovered in the 1970s. The primary radio lobes in winged galaxies are associated with an active jet which is currently being launched by the central engine. The primary lobes often display hotspots that are characteristics of FR2 sources. In fact, winged radio galaxies are actually weak FR2 sources. The secondary lobes are fainter and do not appear to have an active jet or hotspot. The wings can appear diffuse, more disturbed, and may be longer or shorter than the primary lobes. A number of different models have been proposed to explain how the winged radio galaxies are formed. First among these is the spin-flip model, where the X shape is produced when a jet suddenly changes its direction. In this model, the spin axis of the central supermassive black hole changes orientation, which then causes the direction of the jet to change. This may happen when two galaxies merge. As the two galaxies spiral around each other, moving closer and closer until they eventually merge, their central supermassive black holes merge as well, causing the axis of rotation of the resulting merged black hole to be different from that of the two black holes before the merger. If one of the black holes is launching a jet before the merger and the resulting merged black hole also launches a jet, the jet will appear to change direction and the characteristic X shape will be produced. The wings are therefore a relic of the old jet, and the primary lobes trace the path of the new jet following the merger event. This model is very popular as it implies that X-shaped radio galaxies are associated with gravitational waves, which are a natural consequence of the merger between two black holes. The second model assumes that the radio jets interact with their surroundings. Steep density and pressure gradients in the surrounding environment of the jet, along with massive molecular clouds in the host galaxy, may significantly deflect the primary lobes such that they form wings. X-shaped radio galaxies would therefore be very important sources for investigating such interactions involving jets. The third model assumes that winged galaxies are a consequence of the presence of two central supermassive black holes in close proximity to each other at the center of a galaxy. These supermassive black holes have different spin axes and therefore launch jets in different directions. For this model to explain the X-shaped structure, both black holes must launch jets at the same time. Such a scenario may be very rare. There is at least one example of two jetted supermassive black hole orbiting each other in the binary jet source 3C75. But the large-scale appearance of 3C75 is not consistent with an X-shaped radio source because its host galaxy is zooming through the surrounding environment with a velocity of roughly 1200 km per second. Note, however, that none of these models are capable of successfully explaining the shape and properties of all the observed X-shaped or winged radio galaxies. We'll continue this topic of AGN next week. Please do like, share, subscribe, and let me know in the comments what are the topics you'd like me to cover on this channel. I'll see you next week. Until then, take care.